Hey guys, welcome back to another video, and today we're going to be talking about the selection sorting algorithm. This algorithm is pretty easy to understand, so let's look at an example to see how it works. Let's say we're given this unsorted array consisting of the numbers 5, 10, -2, 5, -10, and 3. So our task is to sort this using the selection sort algorithm. We're going to start off by dividing our unsorted array into two different parts. I'm going to do that by using a dotted line. Everything to the left of this line will be considered to be sorted, but everything to its right will be considered unsorted. In the start, we place this line at the very beginning of our array. This tells us that so far everything is unsorted, as everything is to the right of our line. Now we iterate through our list one by one, looking for our minimum value. The current minimum value will be represented in the color green, and the element we are currently on will be represented using an arrow. So we start off with 5, and we make it our minimum value for now. We now compare it with 10, and as 5 is less than 10, 5 is going to remain to be our minimum. Now we have the number -2, and -2 is less than our current minimum, which is 5. So we're going to change the minimum value from 5 to -2. Okay, so now we have -2 and 5, and -2 is less than 5, so nothing changes. But now we have -10, and -10 is less than -2. So we're going to change the minimum value from -2 to -10. And finally, we have the number 3, and -10 is less than 3, so the minimum stays at -10. Now we take whatever our minimum value is, and we place it right before the line we just drew. So in this case, we take our -10 and we place it in the very beginning. Notice that we are not swapping the elements, but we are removing the element and inserting it. This is very important as it helps to maintain the stability of the sorting algorithm. And what this basically means is that we're holding the same order as the parent array. But if we were to simply swap the elements, we won't be maintaining stability. Over here, it's very important to note that normally in a selection sort, we swap the elements, and when you swap the elements, the algorithm becomes unstable. But for the purpose of this video, we are going to try to make it stable. For a more detailed explanation about what unstable and stable sorting algorithms are, I made a short video on this topic which you can check out. Okay, so now we sorted our first element, which is the minimum. So now let's see what happens in the second iteration. In the beginning, we set the first element, which in this case is 5, as our minimum. Our minimum now changes to -2. We now insert our minimum, which is -1, to the left of the red line. By now, I'm sure you can find the pattern. Each iteration, we find the minimum value in the unsorted part of our array, and we add this value to the sorted part of the array. Let's now take a look at how the rest of our iterations are going to look like. Notice when two elements have the same value, we do not change the minimum. The reason for this is again to maintain stability. Finally, we are now done sorting the array. We know we are done since there are no more elements to the right of our line. All the elements are on the left, which is also the sorted side. Let's now take a look at the time complexity for the sorting algorithm. Let's do this by taking a look at the number of comparisons made during each iteration. In our first iteration, we made a total of 6 comparisons. And note that 6 is also the length of the number of elements in the unsorted part of the array. In our second iteration, we made 5 comparisons. For the third iteration, 4, and for the fourth iteration, 3. So this keeps going on for a total of 6 iterations. And we can take this pattern and put it in some sort of formula. We have a total of n iterations, and at the end of each iteration, the number of changes that took place were n minus 1. N over here stands for the number of unsorted elements. When you do this calculation, you get n squared minus n. We are going to ignore the negative n, so we get the time complexity as big O of n squared. So this is its best case, worst case, and average case time complexity. They all have the same time complexity of big O n squared. Altogether, this is a pretty bad and slow time complexity, especially when you compare it with a lot more efficient algorithms. On the other hand, this algorithm takes up constant space, as all of the functions we perform happen in place. Let's now take a look at the code for this algorithm. As I mentioned earlier, the selection sort by nature is an unstable sort. So let's see how that looks like. So over here we have our function, and as our input, we're going to take in an unsorted list, and I call that L. So we're going to start off with the for loop, which starts off at the number 0 and goes up to the length of whatever the unsorted list is. And we're going to set the index which holds the minimum value as I in the beginning. So in the first iteration, that value is going to be 0. After we have that, we're going to iterate from everything starting from I plus 1 all the way up to the ending. And we're going from I plus 1 since we already considered I. You can think of this as the line that we were drawing. And I plus 1 is only going to look at everything to the right of our line. And over there, we're going to look for our minimum value. So this if statement here looks to see if we found something which is lower than our previous minimum. And if that is the case, we're going to change our minimum index to that value. And at the ending of this for loop, we're going to swap the two. We're swapping them. And this is going to cause the sort to be unstable. And at the ending, we're going to return our list. So let's just see what this looks like. As you can see, we have the unsorted array, and we also have the sorted array right below it. Okay, so now let's look at how the stable version of this looks like. So it's going to be the same for the most part. Starting from line 19 all the way until here, it's going to be the same as the stable version. The only difference comes over here. So what we're going to do is we're going to store our minimum value in a temporary variable. So we're storing it over here in a temp variable. Now we're going to pop out that minimum value. And we're going to pop it out by giving that index. And what it's going to do is going to go to the element at that index and remove it. And once we do that, we're going to insert the value. And we're going to insert it by going to whatever I value we currently are on. That's because that I value represents the left of the imaginary line that we have. So we're going to insert it, and I is going to be the index we're inserting it at. So if I value is 2, whatever is going to be at our second index is going to be the value we're adding it to. So in this case, we're going to add that minimum value, which is stored in a temporary variable. And then afterwards, we're going to return our sorted list. And again, if you run this, it should work. So as you can see, we have our unsorted list, and then we have the sorted list. And the only difference between the first and the second one is stability. Finally, let's sum up our video by talking about some of the use cases for this algorithm. And the truth is, there aren't too many use cases. Its only positives are the fact that it takes place in constant space. But the algorithm is really slow with an average time complexity of big O of n squared. There are several algorithms which do what it's doing a lot more efficiently. And finally, thanks a lot for watching, guys. Do let me know what you thought about the video, and don't forget to like and subscribe. Thank you.